In the first part of Notes 12, we looked at what the natural log function is and how to calculate it in SAS. For the second part, we're going to focus on an example that will help to illustrate why the natural log function might be of use to us. If you haven't done so yet, you may want to read case study 3.1.1. It's listed in the additional materials section of Moodle. And it's basically just an example that we're going to look at. So basically, there was a person who was interested in trying to increase the amount of rainfall that they would get. So something that might be useful to, farmers or, anyone trying to stave off a drought or something like that. And they had this idea that if they could inject the clouds with this, I believe it was silver iodide, maybe that would cause the clouds to produce more rain. And so they would send a plane up into the sky on certain days, they would fly through the clouds, they would inject them with this thing, and then they would measure how much rain fell after they did that. So we had some days where the clouds were, it was called seeded with this thing, and some days where they were unseeded. And we're going to compare both of these. And you can see the results ahead of time down here, but let's actually look at it in SAS. So here is the data from the 12-rainfall, and you can see we've got the unseeded clouds and the seeded clouds. That's in a variable that we're calling treatment. And then we've got the amount of rain in a variable that we're calling rain. And this was measured in something called acre feet. So what I'm going to do is first, I guess I will just run the data so we can make sure that it looks like what we want. And it'll just take a second or two here. And now we've got two columns with 52 rows. So here's our rain variable. Here's our treatment, whether the clouds were seeded or not. Everything looks good there. So what I want to do now is I want to look at the normality assumption and the equal variances assumption. And I'm just going to use proc t-test like we've been doing. And this data set is called Rainfall. This is a two independent samples problem, so I need to make sure to include a class line. The treatment variable is the one that splits our data into our two groups. And the variable that I'm interested in studying is the amount of rain. So I'm going to run this, and we'll see that it's going to give me a lot of the output that I need to check these two assumptions. So if I scroll down, I've got my histograms here, and you can see that they're pretty right skewed, and the box plots illustrate that as well. So in both of these cases, a lot of our data is in this sort of lower range right here, and then there's this long tail going out on the right-hand side. So if I go back to the notes, you can see that we said that the histograms are right skewed. We haven't looked at the QQ plots yet, so let's scroll down and look at those. And these points do not at all follow a 45-degree line. We've got a very clear sort of curved shape in both of them that matches up with right-skewed data from a right-skewed population. And so you may remember from the mystery files in Notes 11 that you saw something like this in the past. So that's one issue, is it looks like the normality assumption is not a good assumption for this problem. It does not look like our data comes from populations with normal distributions. We might also wonder about the equal variances assumption, and just sort of visually, we can see that, you know what, this looks more spread out. The data is going a lot further in the top seeded group than it is in the unseeded group, and the box plots actually illustrate that even better. This box plot's quite a bit more spread out than this box plot. We could come up here and compare the standard deviations. The standard deviation for seeded is 650. For unseeded, it's under 300. But we've also learned about this equality of variances test. And if you recall, our null model says that our population variances are equal. Our alternative model says that our population variances are not equal. And we've got a really, really small p-value. So that's essentially telling us that we have very, very strong evidence that the two populations do not have equal variances. So again, if I return to the notes here, what you'll see is essentially we do not have reason to suspect that the normality assumption is a good one to make, and we really don't have reason to believe that the equal variances assumption is a good one to make. And so if this were problems that we had been doing up to this point in the class, we'd sort of have to say, you know what, we're out of ideas. We don't really know how to analyze this problem because we can't make those assumptions that we want to make. But what we saw at the top of the previous page is it's possible for us to calculate the log of one of our variables. And maybe if we analyze our variable in terms of this natural log, maybe our assumptions will be a little bit better. So I'm going to go back to SAS, and I'm going to go to my code. And what I want to do is I want to add a variable that I'm going to call log rain. So this part here is just a name that I'm giving to the variable. And now I need to tell SAS how to calculate that variable. So I am going to take the log of the rain variable. This is similar to when we created a variable called diff, and we told SAS how to calculate the diff, or the difference between two things. All right. So before I actually run my proc t-test again, let me just tell SAS what my new data set is, and you'll see that now I have three variables. I've got rain, I've got the treatment, and I've got log rain. And if you wanted to verify, you could take the natural log of 1202.6, and you should get about 7.09. If you take the natural log of 163, you should get about 5.09. And so you could verify that SAS actually did calculate these correctly. But what I really want to do with this is I want to see if these helped me with those assumptions that were causing me problems. So I'm going to run the same proc t-test code, except I'm going to do it for my log rain variable instead of my rain variable. And I'm going to highlight this and run my code. And if you look down at the histograms, these may not look perfectly bell-shaped, but they look a lot better than the ones did on the previous page. And if I look at my QQ plots, these actually look really good. The points generally follow this 45-degree line. There's no clear pattern where there's like a big curve in either direction. And so the normality assumption seems like it's probably okay at this point. If I want to check whether the equal variances assumption is okay, I can start by looking up here and seeing that both of these are actually kind of equally spread out, especially compared to the original variable. And if I go up to my equality of variances test, instead of having a very, very small p-value telling me that there was really strong evidence my two population variances were not the same, now I've got a really big p-value, which doesn't mean that I know my population variances are the same, but it at least tells me that it's very reasonable that they could be. All right. We'll come back to this at the bottom of this page of notes, but for now, my histograms are much more bell-shaped, so the normality assumption seems good. The QQ plots followed the 45-degree line. Everything looked good there. My two groups seemed like they had pretty close to equal spreads. My p-value for my equality of variances test was much larger than 0.05, and so this assumption seems okay too. And so if we think about why would we want to look at the natural log of rainfall instead of just rainfall itself, we got an illustration of why that might be. In this case, both of our assumptions were not reasonable. However, once we transformed the data, the assumptions were reasonable on our new scale. We'll see later that this isn't always going to happen, but it's a really nice thing to check because a lot of times it can help us out here. So just recapping what we did, we were able to create a new variable in SAS. We added a line of code between the input and the cards line, and I can show you again real quick. I just said that I wanted a new variable called log rain. I wanted to calculate it by taking the log of my rain variable that I already had, and that added this transformed variable to my data set. And so you can take some time to look through these steps here if you would like, and in the next part of the video, we'll work with this example a little bit more and talk about how we might actually interpret our results now that we've got this log transformed variable that we're working with.